Hello everyone and welcome back to Introduction to Number Theory. This time we'll discuss the descent method of solving Diophantine equations. To show you what this method is, let's consider such an equation where x, y, and k are integers. First of all, notice that since the left-hand side is integer, k must be greater or equal than 0. Well, it's not so difficult to prove that if k is negative, this equation has no solutions, no integer solutions. So k is non-negative. Where do we start? Well, first of all, if k is equal to 0, the first case, then the right-hand side is equal to 1. So x squared plus y squared must be equal to 1. X and y are integers. So we have two possible solutions. It either x is equal to 0 and y is equal to plus or minus 1, or x is equal to plus or minus 1 and y is equal to 0 too. So in this case we have four possible pairs, four pairs of solutions, four solutions. The second case, if k is strictly positive, greater than 0, then the right-hand side is divisible by 7, which means that the left-hand side must also be divisible by 7. And as you may remember, if sum of two squares of integers is divisible by a prime number which is congruent to 3 modulo 4, then each of these numbers x and y must be divisible by the same prime number. So x must be divisible by 7 and also y must be divisible by 7. Well, this is a conclusion we can make in case we remember the fact about the sum of two squares and primes congruent to 3 modulo 4. In case we don't remember this, well, it's simply a bit more work to do. We can check all possible remainders of squares modulo 7 to come to the same conclusion. Well, indeed, modulo 7, there are 7 possible remainders. 0, 1, 2, 3, 4, 5, and 6. And if we take each of these remainders and calculate their squares and take the remainder of a square or remainder modulo 7, we will gain, well, 0, square of 0 is equal to 0, 1 gives 1, 2 gives 4, 3, 3 square is 9, but the remainder is 2, 4 square is 16, but the remainder is 2, 5 square is 25, but the remainder is 4, and 6 square is 36, and the remainder is 1. Well, as you can notice, of course, the remainders of squares are symmetric according to the midpoint of this sequence. So all possible remainders of squares of integers, well, any integer whatsoever, its square can be congruent only to 0 or 1 or 2 or 4 modulo 7. And now we return to this place over here. The sum of two squares must be divisible by 7. Okay, so which of these remainders, which two of these remainders can we take to so that their sum is divisible by 7? Well, 1 plus 2, no. 1 plus 4, no. 2 plus 4. We understand that the only possibility is that both x squared and y squared have remainders equal to 0. And this means that x and y are divisible by 7. Since x and y are divisible by 7, we can substitute, say, let x be equal to 7x1 and y be equal to 7y1, where both x1 and y1 are integers. Substitute this into the initial equation. And we understand that after dividing the initial equation, after substituting and dividing the initial equation by 49, which is 7 squared, we will get an equation which looks very alike the initial one. x1 squared plus y1 squared will be equal to 7 to the power k minus 2. Look at this equation here. Look at that equation there. They're the same. Well, simply another letters. Here we use letters x, y, and k, and here we use, well, variables x1, y1, and k minus 2. But the equation is the same. What does this mean? The same equation. Does this mean that all this was for nothing and we simply are stuck with this equation? Well, no, because we are studying number theory. And in number theory, we're dealing with integers. And we understand that x1, y1, and also k minus 2 are less than the initial x, y, and k, because x1 and y1 are, where their absolute value is less, strictly less, than the absolute value of x and y. Well, of course, unless they're equal to 0, but it is just a particular case. So we understand that we can continue this procedure, these two cases, with the new equation. And we will gain the new equation, new equation, x2 squared plus y2 squared will be equal to 7 to the power k minus 4, where, of course, x2 is x1 divided by 7, y2 is y1 divided by 7. And so we can continue this way as long as we can. But how long will this last, and what will happen in the end? We understand that the power of 7 is decreasing. It's decreasing by 2 each step. So eventually, well, since we know that k is non-negative, this power should be non-negative. Eventually, we will arrive either to the case where k is equal to 0, or to the case where k is equal to 1. Let's consider this case separately. Well, if k is equal to 1, then our equation looks like a square plus square equal to 7. But we already know that if sum of two squares is divisible by 7, then each of these is divisible by 7. So the sum of two squares is divisible by 49. So we understand that this equation has no solutions. Well, if x and y are integers, then x and y belong to an empty set, which means that there are no solutions. So finally, I believe we are ready to give an answer. What we know? We know that dividing both x and y by 7 several times will bring us either to such equation, and then we will have no solutions, or to such equation where k is equal to 0. And in that case, we will have these solutions. So eventually, we can say that x and y, one of them, well, first we start from k. K must be divisible by 2. So we can say that k is 2l, for instance, where l is non-negative. And x and y, one of them is equal to 0. And the other one is equal to plus or minus something. Well, what something? Okay, when k is equal to 0, when power of 7 is equal to 0, then it's plus or minus 1. But in the beginning, it was plus or minus 7 to some power, because on each step, both of them were divided by 7. So dividing, well, say y by 7 several times brings y to plus or minus 1. This means that initially y was equal to 7 to the power, well, now it's already obvious that 7 to the power of l. This notation here means that either x is equal to 0 and y is equal to plus minus 7 to the power of l, or the other way around. Our equation is solved.